Hello students, in this video we'll discuss how to use the eigenvalue method to find straight line solutions to dynamical systems. To find a straight line solution, to the system x prime of t is a x of t, where here A will be an n by n matrix and x will be an n by 1 vector. We set x of t to be a constant vector v e to the lambda t. Plugging this into the differential equation, we will see that the derivative of this straight line solution with respect to t will be x prime of t will be v lambda e to the lambda t, and this has to be equal to a v e to the lambda t. Now there is an e to the lambda t on both sides of the equation, so that will cancel out. And we see that in order to find straight line solutions, we must have that a v is lambda v. And this is our eigenvalue equation. To find the eigenvalues, solve determinant of a minus lambda times the identity matrix equals 0. This is our characteristic equation. Once we find the eigenvalues, we can plug them back into this eigenvalue equation to find the vectors v along which the solution will be a straight line. Let's see an example of this. Let's solve x prime of t is the vector negative 9, negative 3, negative 3, negative 9, x of t, by finding the eigenvalues. And the eigenvectors. So we solve our characteristic equation. We set the determinant of our matrix A, negative 9, negative 3, negative 3, negative 9, and I subtract off the matrix that has lambdas in the diagonal and 0 everywhere else. Lambda, 0, 0, lambda, and I set this equal to 0. So we see that this is equivalent to solving the problem. Determinant of negative 9 minus lambda, negative 3, negative 3, negative 9 minus lambda equals 0. To do the determinant, we multiply the diagonal entries and we subtract off the off-diagonal entries. If I multiply the diagonal entries, I will have 9 plus lambda quantity squared. And then I'll have a negative, negative, negative 3 times 3. So that will be a negative 9 equals 0. And we can solve this equation. This will tell me that 9 plus lambda squared is equal to 9, or 9 plus lambda is plus or minus 3. So this is going to be 3 or negative 3. This tells me, therefore, that lambda, so if lambda plus 9 is equal to 3, I'll have lambda equals negative 6, or lambda equals negative 12. So I've found eigenvalues of negative 6 and negative 12. And now I'll find the corresponding eigenvectors. So, to find the eigenvector corresponding to lambda equals negative 6, we plug it back into our equation. And if I have negative 6, this is negative 9, then a negative negative 6 is a positive 6. So my matrix will become a negative 3, negative 3. Then I'll have a negative 3, negative 3. I need to find a vector v1, v2. That gives me 0, 0. And we can see from this that I can choose the vector v1, v2 simply just to be 1, negative 1. So I have my first straight line direction solution. The second case is lambda is equal to negative 12. In this case, I'll have what vector? I'll have negative 9, then negative negative 12 will be positive 12, so I'll have a positive 3, then a negative 3. Then I'll have a negative 3 and a positive 3 applied to v1, v2, giving me 0. And we can see from this that I can choose v1, v2 in this situation to be the vector 1, 1. If I choose the vector v1, v2 to be 1, 1, I'll have the first row dot the first column being 0, and the second row dot the second column being equal to 0. Now I have found two straight line solutions. So I have one straight line solution will tell me that x1 of t is c1. This corresponds to negative 6, so I'll have e to negative 6t in the direction of 1, negative 1. And I'll have a second straight line solution, x2 of t is c2 e to negative 12t in the direction of 1, 1. And to find the general solution, we just add these solutions together. So the general solution to our problem, x of t, will be c1 e to the negative 6t, 1, negative 1, plus c2 e to negative 12t, 1, 1. So by using this eigenvalue method, I was able to find two straight line solutions to my problem. Once I have two solutions to a second order equation, I can take a linear combination of those things to find a general solution. One thing we should also note from this problem is that as t approaches infinity, both e to the negative 6t and e to the negative 12t tend to 0, so x of t will approach the 0 vector, which tells me that this is a stable equilibrium at the origin. Thank you very much.